At the beginning of this unit, we looked at a bridge that was built on principles of tensegrity, where there were members of the bridge that were pulling on each other, and it was through tension, through those tension forces, that it held together. Here we see another example of tensegrity. This is a tensegrity sculpture on the right, and if you look at it, you see that none of these solid members, or I guess they're probably tubes, but none of these parts are actually in contact with each other. They're held together by cables. Those cables, which normally don't hold, well, they can't hold things up by pushing on them, right? Cables are flexible, but by putting competing tension forces in this structure, it creates a really interesting sculpture. This is a question. It's a phenomenon to consider as we learn things in this unit. We're not going to answer this right now, but there's a question. Why is the fall and impact of a small, lightweight object different from the fall and impact of a more massive object? For example, why can an ant or a spider fall from a great height and just walk away without being killed? Ants can fall from many times their own height and not be injured, whereas a person or a larger animal would be injured. So let's think about that. And it has to do with the forces experienced by that ant or spider. We've talked about representing motion as in vector form. Forces are also represented using vectors quite a lot. We're going to be drawing a lot of vectors. A force is defined as a push or a pull. That's a very simple definition. That's why the title here says pushes and pulls. But when you think about a force, I don't want you to associate forces just with a motion. Okay, I want you to associate force with acceleration. When a net force is applied to an object, it will accelerate. And remember, acceleration is any change in velocity. So a force is required to cause something to speed up, to slow down, or to change direction. Force and acceleration always go hand in hand. If there is a force, if there is a net force, there will be an acceleration. If there is an acceleration, there must be a net force. So those two things go hand in hand, and we'll see this spelled out when we look at Newton's laws of motion. A very simple definition of a force is a push or a pull. And a force is typically caused by some other object in the environment. Now, a force can be caused by an object in contact with the object in question. So, like if you push something and it slides across the floor, you're applying a force to it. But a force can also be applied from a distance. If you drop a ball, it falls toward the earth because the earth is applying a force from a distance, but something is applying a force. One kind of force is friction. Friction is a force that always opposes motion. So it will either stop something from moving. The reason things don't go sliding all over the place is because there's friction between the floor or the ground and that object. That's why you're able to stand on your feet, because there's friction between your feet and the ground. So friction can hold something in place, or it can work against motion. If you roll a ball across the floor, or let's say if you slide a hockey puck across the ice, eventually it's going to slow down because there's very low friction between the hockey puck and the ice. There's low friction between the ball and the ground, but there is still friction, and friction acts between the surfaces of the objects that are in contact. So friction doesn't speed things up. Friction slows things down. It's a force, and that is important. Friction is a force. This is one force. You defined several different kinds of force before, but friction is a force that opposes motion between two surfaces that are in contact. If you look at page 26 in your textbook, or you look at your Explore Explain that you did online, you'll see a description of several different kinds of forces. So gravity is the force between two objects. Usually when we talk about gravity, we're talking about gravity between the Earth and something near the Earth. But gravity is a force that exists. It's a field force that exists between two objects, and it's always an attractive force. Normal force is a force that exists between an object that's sitting on a surface, and the surface pushes back up on the object. Gravity pulls the object down. Let's say a book is sitting on a table. Gravity pulls the book down. The table pushes the book back up. The table is providing the normal force. A spring force is a force where something changes its shape and it has a tendency to return to its original shape. So it might be a spring that gets compressed and pushes back out. It might be a rubber band that you stretch and then it wants to return to its original shape. A tension force is a pulling force. So if you're pulling on a rope, that is a tension force. Or in the tensegrity sculpture, we saw cables being pulled on. Those were tension forces. Okay. The normal force, as I said, it's a force that acts. So the normal force, let me draw a ground here. We need a ground between. Okay, so this car is sitting on the ground. We have gravitational force, right? The gravitational force is the weight of the car. So we have a gravitational force, force of gravity, pulling down on the car. The earth is pulling down on the car. But then the car is not accelerating down, right? It's not falling. So that means that something must be pushing it up to balance that force. The ground is pushing up on the car. That is the normal force. So we have the force of gravity pulling down on the car. We have the normal force pushing up on the car. And so we can say that if this car is not accelerating, right? It's not falling. It's not flying up in the air. The forces on it are balanced. And this is where we see that vocabulary term. The forces are in equilibrium. Okay, balance, when forces are in equilibrium, we say they are balanced. Now, weight is the effect of the force of gravity on the car. So what we call the force of gravity, we can also call the weight of the car. Weight and mass are not the same thing. Mass, remember, is the amount of matter the car is made of. Weight is the force of gravity on the car. So they are related to each other, mass and weight. They are not the same thing. Mass is a scalar. Weight is a vector. Weight has a direction. Weight is always directed down toward the earth because it's the earth toward the center of the earth, because the earth is pulling on the object with the force of gravity. On page 27 or in your Explore Explain in your electronic textbook, you saw some terms that about forces. It says in a free body diagram, the force on an object is represented by a vector. The length of the vector is proportional to the size of the force. Suppose you push a wheelchair forward at a constant velocity. The wheelchair is not accelerating, so the forces are balanced. In a free body diagram of the wheelchair, the vector of the force due to gravity points down. The vector for the normal force points up. The vector for your force pushing the wheelchair points forward. And the vector for the force of friction resisting the motion points backward. So we have four different forces acting on this wheelchair, but since those forces all add up to 0, they are balanced, and the wheelchair is not accelerating. What happens when forces are unbalanced? Well, if you add up all the forces, if you add up all the vectors, you find the resultant of all the vectors, and the sum of those vectors is not 0, then we say that we have an unbalanced force or a net force. We can say an unbalanced net force. So that's another vocabulary term. So we have a non-zero net force on the object. And when you have a non-zero net force, when you have an unbalanced forces, then the object will change its motion in the direction of the net force. Change in motion, another way of saying that is that it will accelerate. Accelerate. And remember, accelerate in everyday language, we usually mean speed up. But in technical language, accelerate is any change in motion. Acceleration is any change in motion. So it can mean speed up, it can mean slow down, or it can mean change direction. On page 28, you see several scenarios where a box is starting from rest and then its motion is changing. So then the question is, what direction is the net force, and how will the box change its motion in response? Well, in the first example, we see that the box is falling. If the box is falling, then that means it's accelerating downward. So it has a net force downward. It has two forces acting on it. It has a force of gravity pulling it down, and then it has air resistance pushing it back up. In the second example, we see a box attached to a rope hanging from the ceiling. Okay, so this is, in this example, we see that the downward force, the downward net force is longer. The downward vector is longer than the upward vector. So the downward vector represents gravity. The upward vector represents tension, the rope pulling back up on the box. But since the downward force, the gravitational force, is greater than the tension force, that tells us that the box is accelerating downward. In other words, the box was too heavy. Gravity has broken that rope, and the box, since there is a downward net force, the box is going to accelerate downward. In the third example, we see a box bouncing on a string, and the upward vector is greater than the downward vector. So that means that the box is accelerating upward. The spring is pushing the box up. The gravitational force is pointed downward, and the arrow pointing up is the spring force. Oops. Okay, now here we see a diagram, and this diagram is similar to the diagram you see in your textbook on page 29. This shows multiple forces acting on a box on a ramp, and this is a typical physics problem that you would see. What we see here, this drawing that we see is called a free body diagram. A free body diagram. And free body diagrams are great. They help us determine the net force on an object. A free body diagram doesn't show all the forces in a picture, right? It just shows, like, it doesn't show the forces acting on this ramp. It only shows the forces acting on, it shows the forces acting on one object. And that's important. If you wanted to show the forces acting on the table, you would draw a separate free body diagram. So a free body diagram shows all the forces acting on one object, and that helps us because now we can add these vectors together and we can find out what the net force on this box is. When you're drawing a free body diagram, start with gravity. Okay, gravity is pulling most objects down toward the earth. And then the normal force, if the object is sitting on a surface, then there's a normal force that's perpendicular to that surface. And since this box is sliding down a ramp, there is also a frictional force. Now, I can see that it's sliding down the ramp, but in order to really determine you would see a similar diagram if the box was sitting still on a ramp. We would just see a longer friction vector. So in order to figure out if the box is sliding down or sitting still on a ramp, we really have to create this free body diagram and see which direction the net force is. Just from experience, I can see that the net force is going to be pointing down the ramp. But you'll learn how to do this over time. So vector addition is used to combine the forces, or they can be represented mathematically. So what we'd have to do is we'd have to find the net force on this object. So if we take this gravity force, we can already see that, and we'll learn this, we'll get practice with this, but we can already see the normal force and the frictional force are perpendicular to each other. So let's break the gravitational force down into its component vectors that are parallel to the normal force and the friction force. Because when we do that, we can see what the net force is going to be. Remember the force of gravity. Any vector can be broken down into its component vectors. And so if we look at gravitational force, we can see that the net force on it, okay, the y component, we can call this F sub gy, is going to, when you add that to the normal force, they're going to add up to 0. So this force is going to cancel out. This force is going to, oops, not that force. I can't erase that, but let's say this force. This force is going to cancel out. And so the only forces we're going to be left with are these forces that are parallel to the ramp. So we have this little friction force and this larger force pushing the box down the ramp. When we add these two forces together, okay, we add this long force to the friction force, which is about this long, we find that the net force is actually this force. Okay, so that tells us that if this is the net force, let me make it, okay, well, if this is the net force, then that tells us that the box will accelerate in that direction. It will slide down the ramp and it will speed up as it slides down the ramp. We're going to do a lab in class, and so you will apply what you learn in this lab, testing the friction of different materials to our next bit of learning.